Yes, we can start.
Thank you very much, Arvid. So we have 3 more lectures. This lecture, this hour, I will speak about strong monotonicity and irreducibility. I think this is interesting because it's a topic really about the transmission of information in a network and the fact that some communication network must be connected in order for this transmission of information to work. So I do want to speak about this in a little detail. And of course, it's important for the RFM and for networks of RFMs. Then I will say a few words about the case of stochastic rates very shortly. Then we will speak about networks. And if we have time, maybe I will say a few short words about something called the gain of entrainment, or GOE, which is something that evolved in the study of the RFM, and I think that's interesting as well. And also I have slides for this, so maybe it will be easier to follow. I will not write on the board, but show you a presentation that I prepared once for some conference here in Israel. So anyway, let's start with monotonicity and strong monotonicity. And as usual, you are very welcome to ask questions. I know that it's a Friday, and the last lecture is even quite late in Friday. So thank you first of all for anyone attending. And if you have questions, please don't hesitate to barge in and ask me. And one last thing before we start, I reminded you that today, just in this lecture, I have to finish 5 minutes early because I need to do something here in Tel Aviv University. So I'll finish 5 minutes before the end, the official ending. Okay, so what is monotonicity? We have a dynamical system. If we fix 2 initial conditions, which are ordered, and then we say that the system is monotone if this holds for all t. So the flow preserves the ordering between the initial conditions. And what is strong monotonicity? Strong monotonicity means that if you fix 2 initial conditions which are not equal, of course, if they are equal, all this is meaningless, because if they are equal, these are also equal. So imagine they are not equal, and this forces XTP to be strictly smaller than XTQ for every time positive. And this notation means that every entry, X1 here is strictly smaller than X1 here, X2 is smaller, X3 is smaller. So the inequality, the weak inequality becomes a strong inequality. The system somehow propagates the information. What is this? What is this? What does this mean? This means that you have P and you have Q. Some of them maybe are equal, but there is at least one entry where P is strictly smaller than Q. Let's say entry number 3. And then this says that this information somehow propagates, and after infinitely short time, we have strict inequality in the solutions. So this is the meaning of strong monotonicity. For a linear system, we have monotonicity if and only if A is a Metzler. And today what I want to show you that for strong monotonicity, we need A Metzler. So if we take a linear case for the dynamics, then strong monotonicity is implied by A Metzler and irreducible. I think this is actually an if and only if. So this is what I want to show you. As I said, I will go through the equations because I think they're interesting. I think it's interesting to understand why irreducibility is needed and what does it give us. let me remind you what is a reducible matrix. A is called reducible if there is a permutation matrix that brings us into this form. K is at least 1 and up to n minus 1, FG0H. So this is when there exists a permutation matrix P that brings us to this form with K between 1 and n minus 1, we say that A is reducible. And if there is no permutation matrix that brings me into this form, then A is irreducible. This is the property that we need, irreducibility. By the way, is the screen okay? And can you hear me and see me? Hello? Anyone out there in the big world?
It's fine.
It's fine.
Site is totally fine. No problem.
Thank you. Excellent. Thank you very much. Okay. So let me try to explain what this reducibility means. What does reducibility mean? Let's take an example. Let's take an example for when n is equal to 3 and k is equal to 2, just for example. So what does this mean? Here I have a 1 by 1 entry. Here I have two entries, G1, G2. Here I have n minus k, n minus k. No, sorry, this is 2. F1, F2, F. So this will be F1, F2. This will be G11, G12, G21, G22. I'm considering a case where, just a minute, let me fill it up and then I will explain. H1, H2. Let's consider an example where the system is reducible, even without permutation matrix. Assume that A has this form, then this is reducible. I took parameters just to make life easy, n equal to 3 and k equal to 2. Let me just make sure that I'm okay with the, no, I'm not okay. Because this should be k by k. Okay, that's okay. This should be k by k. This should be k by n minus k. K is 2. N minus k is 1. K is 2. K minus 1 is 1. So like this. I'm sorry. This is F11, F12, F21, F22. This is 1 by 2. So this is G1, G2. This is H n minus k by n minus k. A minus k by A minus k is like this, and this is like this. So I filled up all the entries of the matrix for this particular example. So the block of zeros here is just these two zeros. And I want to explain what this means. So let's generate the adjacency graph for this matrix. And what is this adjacency graph? I see that there is a, so I label the rows by 1 to 3, and I label the columns by 1 to 3. And when I see an entry here, which is not necessarily 0, from 1 to 2, I draw an edge from node 1 to node 2 with the weight F12. This is this entry, which is in general not 0. Only these are zeros. And here I see an entry from 1 to 3, which is G1. And here I see from 2 to 1, which is F21. Here I see from a node to itself, it doesn't matter. Now we have from 2 to 3, G2. These are zeros, so I don't mark them. And now from 3 to 3, I don't mark either. And now, what do I see? I see that there is a node here, node number 3, that only accepts information, but never provides information. So the network, since A is reducible, the corresponding graph is not connected. In what sense is it not connected? I can go from here to everywhere, but once I reach node number 3, I cannot go back. From node number 3, there is no going back because of these zeros. So reducibility means that when I look at the associated graph, I see some small bundle of nodes that are not that do not provide information to the rest of the network. Nodes 1 and 2 can never know what is going on in node number 3 because the communication is from 1 and 2 to 3, but never back. This is the meaning of reducibility. And this part, this is just relabeling of the nodes. So this is meaningless. Up to relabeling the nodes, the graph is not connected. This is equivalent to reducibility. So this is just an intuitive explanation of what reducibility is in terms of the graph. Somehow there is not enough communication between the nodes, and because of that, we will not have strong monotonicity. When the network is irreducible, when A is irreducible, then we will have enough communication to guarantee strong monotonicity. So I want to give now a lemma which considers, this is lemma 2 in chapter 3 in the nodes, and we consider a time-varying linear dynamical system first of all. Later, we will study a nonlinear system, but it's always good to start with a linear system. And we assume that this matrix is a continuous function of time. So we have a time-varying matrix, but let's assume it changes continuously with time, so it doesn't jump. And let's assume that AT, Metzler, and irreducible for all t. Let's say that we start from type 0 for simplicity. So the initial condition is at type 0. So irreducible means that it is not, this is reducible. This is the situation where there is not enough communication. Irreducible means that there is enough communication, and then we want to show the following. If V0 is larger or equal to 0, and it is not 0, of course, if it is 0, if this is 0, if we start at 0, we stay at 0. So this is not a very interesting case. But let's assume that V0 is larger or equal to 0 and not 0. Then Vt is strictly larger from 0 for any positive t. So this is strong monotonicity. We start by V0 larger or equal to 0. So some of the entries are 0, but because of this, not all the entries. At least one entry is positive. And this says that as we consider the solution for any time positive, all the entries are positive. This means that all the entries are positive. So the information from here to here, after any short time t, all the entries of V become positive. This is exactly strong monotonicity. This was exactly the condition we needed, that if there was here at least one positive entry, this means that there is at least one positive entry. Here already all the entries are positive. And let me give the proof of this because it's not difficult. And the proof, and I think it teaches us something. And the proof includes two steps. Step 1, we show that if Vi0 for some index I is non-negative, we show that if this holds, then this also holds. So the first part of the proof, if for some index I, the first part of the proof is like this. If we have some index I such that this is positive, then it will remain positive forever. So we don't have to worry about the positive indexes. The positive entries are guaranteed to remain positive for all eternity. We just have to look, what this means is we just have to check what happens with the entries that are 0 at time 0. All the entries that are already positive at time 0 will remain positive. And what is the proof of this? The proof goes like this. Let's calculate the derivative of this VI. VI dot. This is sum AIJT, sum on J of VJT. This is simply because of this dynamics. VI dot is the product of row I of the matrix A with the vector V. This is exactly what I wrote here. And now let's break this into two pieces. AI IT VIT plus sigma on J, but now J different from I, AIJT VJT. Okay, let's look at this. First of all, I claim that all this is a non-negative term. Why is it non-negative term? The matrix is Metzler. The matrix is Metzler, and here I have entries Aij with J different from I, so all these entries are non-negative, because these are exactly the off-diagonal entries of A, and because the matrix is Metzler, the off-diagonal entries are non-negative. And also, because we started here with an initial condition which is not 0, which is larger or equal to 0, and the matrix is Metzler, we know that VT always remains larger or equal to 0. This is just because of the Metzler. This is monotonicity. We need to prove strong monotonicity, but monotonicity we already know that it holds. So this is also non-negative. So all this term is non-negative, and we conclude that this is larger than AIT VIT, larger or equal to this. Now, what does this mean? I will write here. Let me erase this. I will continue again. What does this mean? This means that VIT is at least the integral 0 to T AIISDS VI0. VI0, we assume that it is positive. This is also always positive. So we get that this VIT is positive for any T. Okay, so we have a bound here. This is just a scalar differential equation, and we have a bound here with the lower bound equal to AIIVI. And this means that we have this bound. This is an exponential, so it is always positive. And this is also positive because we are now considering any index, an index I, for which this was positive, so it remains positive. So this proves step 1. If you start from a positive entry, VI0 positive, it will remain positive forever. This can, if AI is negative, this can converge exponentially to 0. It is possible, but for any positive, for any finite time, this is still positive. So I erase this with your permission and move to step number 2. Questions about step number 1 before I erase it? Okay, so step number 2. Step number 1 showed us that any entry here which was already positive at time 0 will remain positive forever. And that's good, because now we only have to worry about the entries that were 0. Step number 2. So what is step number 2? Since V0 is larger or equal to 0 and V0 is not 0, there exists an index J such that Vj0 is positive. There is at least one positive entry Vj. Let S be the number of indexes such that the number of indexes J or the number of indexes K such that Vk is positive times 0. So we know that there is at least one such index because of this condition. Maybe there are S indexes, or we denote the number of indexes for which Vk is positive by S, and then S is larger or equal to 1. If S is equal to n, then Vi0 is positive for all I, and by step 1, Vit remains positive for every t. And then we are done. This is what we wanted to prove. We wanted to prove that all the indexes are positive for all time. If we started from n positive indexes, so if, this is like saying if actually here we had this, because in step 1 we proved that what started positive remains positive, then everything will remain positive and we are done. So let's assume that S is not equal to n. We know it is at least 1, and let's assume it is not equal to n, because if it is equal to n, we are done. So let's assume it is smaller than n, and without loss of generality, assume that the first S indexes are the positive ones. If not, we just reorder the vector, nothing will change, because reordering the vector is like applying a permutation, but the condition for irreducibility holds for any permutation. The condition said that for any permutation, we don't have this block of zeros. So we may assume without loss of generality that the S positive entries in V are the first S entries, and the other entries, because S is exactly the entries which are non-zero, all the other entries are 0. Now, let's consider V dot ATV in this form. We decompose into V1 dot, I will not write of T now, just for simplicity. Let's decompose the vector V in this way. And let's decompose here the vector V in this way. We separate, first of all, the first S coordinates, and then, which are positive at time 0, and then the other coordinates, which are 0 at time 0. And here I divide into blocks of the same dimension. So this is S n minus S, S n minus S. I divided A into 4 blocks of these dimensions corresponding to the way I broke the vector V, and I gave each block a name. And everything depends on time, but I just don't want to write it to save us energy. Now, since the matrix is irreducible, okay, look, this is Metzler. Why is this Metzler? These are the diagonal entries, because this is an S by S block. The diagonal entries are here. These are off-diagonal entries. The entries in K are off-diagonal entries, and because the matrix is Metzler, K, all the entries here are non-negative, because A is Metzler, and because these are, by construction, off-diagonal entries. Now, the matrix is irreducible. This is where I use the fact that the matrix is irreducible. So by irreducibility, I erase here with your permission, by irreducibility, at least one entry of K is positive. If all the entries of K are zeros, then the matrix is reducible. This is exactly the definition of reducibility. If you have a block of zeros of dimension n minus s by s. But we assume that the matrix is irreducible for all t. Therefore, this block, which is Metzler, so all entries non-negative, cannot be zero. So there is at least one entry of K which is positive. But now, what does this mean? This means that when I look at Vs dot Vs1, so now look at these entries. They are given by K multiplied by V1 up to Vs, right? Because of the way I decomposed the matrix. Now, these are all positive. Why? They were positive as zero, and we already showed that if something was positive as zero, it is positive for any time. This was step number one. The entries that were already positive remain positive forever. So these are all positive. The matrix K is non-negative and at least one entry positive. So the conclusion here is that the conclusion is there is at least one derivative here which is positive. Why? I multiply this matrix, which is entry-wise non-negative, but at least one entry is positive by this all positive vector. And then this means that at least in one row here, the row where I have the positive entry of K, I will get a positive derivative. But if I get a positive derivative, then one of these becomes positive immediately. So one of Vs plus 1 t Vnt becomes positive immediately at time t positive because it was zero, these were zero, and now they have a positive derivative. All these are zero. One of them has a positive derivative, so it will become positive immediately. So from S positive entries, we actually grew to S plus 1 positive entries. We had S positive entries here, but because of this communication transmission from the positive ones by K to these, which are negative, we immediately guarantee that another entry, one of the entries here, also became positive. And we know that it will remain positive forever. But then the same argument exactly says that immediately another new positive one will be born. Because again, now we look at the S plus 1 positive entries and what is left. And because the matrix is reducible, they will transmit the information and get another positive entry and so on and so on. So the conclusion is, so we conclude that V, T are all positive entries for any positive T. This is what we wanted to prove. So the key point here is that because the matrix is irreducible, these entries, which are 0 at time 0, receive positive feedback by K multiplied by this. These are the positive entries. And this matrix is non-negative component-wise. And because of irreducibility, at least one weight here is positive. And when we multiply it by this, we get positive information. So the irreducibility means that these state variables, which are not positive yet, get information from these state variables, which are already positive, and then immediately a new positive state variable is born, and then another one and another one, and we see that for any positive time t, all the state variables become immediately positive. So I think it's a nice proof in the sense that it shows you exactly how this issue of irreducibility leads to better transmission of information, and then from the non-negative, from the positive entries here, even if there is just one, everything becomes positive immediately, and then we have strong monotonicity instead of just monotonicity. And again, it is all based on the structure of communication between the variables. And this is important because in many problems of where you have a lot of agents and they communicate with one another, this issue of irreducibility guarantees that somehow there is a communication, there is no separated group that does not receive information. They all interchange information all the time. And in many cases, this has important applications, like here. Okay, so this was the proof of lemma 2. Questions, if any? Please don't hesitate to ask. It's a good time to ask questions. I know that this is a little heavy. I just want to complete this proof for nonlinear systems. The next part is easy, really. And then the rest of the talks today, since it's a Friday, these are the last talks, they will be a little lighter, I hope. Okay, so now let me
Hello, Michael. Good morning.
Okay.
Michael, apart from the condition of Metzler and irreducibility, is there any other conditions that guarantee strong monotonicity? Are they sufficient or necessary conditions for the strong monotonicity?
I don't know of any other condition. The Metzler is certainly necessary because the Metzler guarantees this. Yes, this follows from the Metzler. So the Metzler we certainly need. If we don't have Metzler, we don't even have this. So certainly we will not have the stronger condition. And I think you need irreducibility because otherwise you can have there in the block K, you can have a block of zeros, you can have a block of zeros here. And if you have a block of zeros, the information will not propagate and these will remain zero. These entries of the vector will remain zero, and then we will not have this property. So I think that, that you can transform this under some conditions on the regularity of AT, you can actually make this, I think, a necessary and sufficient condition. You need, I think, both the Metzler and the irreducibility. I think so.
Means if and only if condition we can prove the other way, maybe after some.
Yes, yes,
Okay.
yes.
Okay.
Yes, you just need some continuity in A, so there won't be all kinds of strange jumps. But I think you can make this into an if and only if statement. For our purposes, it's enough always to state it in this direction because we just need to know that this holds. But I think that you can make it into an if and only if. Thank you.
Okay.
Okay, so let me now give you theorem 10 that speaks about strong monotonicity in, okay, let's do it like this. I will erase everything here. I will keep just the linear results because we will need it when we study nonlinear systems. So this I keep on the board. This is strong monotonicity of a linear system. And now I speak about nonlinear systems. So theorem 10 says the following. We now consider a nonlinear system if Jx, Jacobian, is Metzler and irreducible for all x in the state space, of course, then the system, the nonlinear system, is strongly monotone. So again, all we need to check is that some matrix is Metzler and irreducible. But now this matrix is just a Jacobian, which is not surprising because we already saw that when we wanted monotonicity of this, when we wanted this to be a monotone system, not strongly monotone, we needed J to be Metzler. And now we add the reducibility, and then we get strong monotonicity. And let me give the proof because it relies on this and it's not complicated. So let me give the proof for nonlinear systems that relies on the linear case that we already proved. So the idea is like this. We have to make one definition, one construction, say. We pick initial conditions A, B with A smaller or equal to B, A not equal to B. Now, what do we need to prove? Let me just write. What do we need to prove? We need to show now, in order to guarantee strong monotonicity, what does it mean? Excuse me, I bought better pens. What do we need to show? I'm just writing here with a question mark. We need to show this for every positive t. This would imply strong monotonicity. We take two ordered initial conditions which are not equal, and strong monotonicity would mean that for any positive t, the condition between the x's is now a strong inequality like this. That's what we want to show. So how do we show this? First of all, we define a line between A and B, between our two initial conditions. Let's define the line between our two initial conditions. So if A is here somewhere and B is here, gamma R is this line connecting the two initial conditions A and B. And now we define another quantity, which I will explain. This is d to the r xt gamma r. Let me explain what this is. Here you take an initial condition along the line, you fix some r between 0 and 1, and then you are somewhere along the line. This is your initial condition. Then you run the dynamics for t seconds, and you get to some location, xt gamma r. And then you differentiate this with respect to r. So this means if I make a small change in r, I shift a little bit here along the line. I change a little bit my initial condition along the line gamma r, and I check after t seconds what was the influence on the solution after t seconds. So if I define W like this, what are the implications? First of all, W0R, this is for any R, I can define this for any R in 0, 1. Omega 0R is d to the R x0 gamma R. What is this? Let me write a little larger so you will be able to see. I want to explain two implications of this definition. The first implication is to consider what happens if you take initial condition 0 in your WTR. WTR is like a state variable. It's like a state. It's a vector that depends on time. It's a vector that depends on time. And I want to understand its dynamics. So first of all, what happens at time 0? Time 0, I substitute here 0, but if I start at time 0 in gamma r, this is my initial condition, and I follow the solution for 0 seconds, then I am just at gamma r, because gamma r was my initial condition, and I ran the dynamics until time 0, I just left at gamma r, and by the definition of gamma r, this gives me b minus a. This is good because this is a non-negative vector by this assumption of my initial conditions. And the second application of this definition, let's write it here. Second application, let's calculate d dt WTR. So by definition, this is d dt ddr xt gamma r. I want to understand the dynamics of this W. So by definition, it's like this. Under some mild conditions, I can replace the two derivatives. I don't speak too much about all kinds of technical conditions that are needed for this. I don't want to be too technical. So I replace the order of the derivatives. And now, what is this x derivative with respect to time? This is just f, because this is my dynamics here. The derivative with respect to time of x is just to apply f. So I didn't write a very nice f, but this is f. Now I apply the chain rule. So let me shift this to the side. W0R is b minus a, which is larger or equal to 0. This is for any r 0, 1. R can be arbitrary in 0, 1 along the line. Now, what is this? I use the chain rule. The chain rule tells me that I have to differentiate xt gamma r, and then I have to differentiate what's written inside here by r. This is just chain rule. You make a small change in r. This generates a change in x, and this generates a change in f. So it is enough to consider, first of all, what was the change in f. I differentiate f with respect to x, and then to differentiate the x with respect to r, and this gives me j multiplied by w. So I don't write now all the entries. This is just j multiplied by w, because this is exactly w by definition. So I got w dot equal jw, a linear system with initial condition which is non-negative, and I know that my j is Metzler and irreducible. So if my j is Metzler and irreducible, and I start from an initial condition which is larger or equal to 0 and is not 0, okay, I should say here, this is not 0 because this was my assumption, then I know from lemma 2, I know that from lemma 2, by lemma 2, I get that WTR is strictly positive like this for any t and for any r in 0, 1. I got to the situation which is exactly the situation of a linear system. J changes with time, so it's a linear time varying system. But since I assume it is always Metzler and irreducible, I can apply lemma 2 and get this condition. This is again a linear system starting with a non-negative vector, which is not 0. And because this is Metzler and irreducible, I know that the vector will become positive, strictly positive like this, after arbitrarily short time. And now we are very close to finishing. Okay, so this I can erase. Right? I needed this just to prove now lemma 2. I'm sorry that the board is a little small, so I always have to erase something and write something new. Now, let's calculate xtb minus xta. This is exactly what I need to show, that this now became strictly positive. But this is ddr xt gamma r dr. So this is again this old trick of differentiating this with respect to r and integrating with respect to r by the fundamental theorem of calculus. When I differentiate something and integrate something, I just get something at the upper limit, minus at the lower limit. So with the upper limit, gamma r is just, when r is equal to 1, this is just b, so I get xdb. And in the lower limit, minus at the lower limit, the gamma r when r is equal to 0 is just a. So I get exactly xdb minus xda, but now this is useful because this is my w. And my w I already know is all the time strictly positive. And then when I integrate on a vector which is strictly, all the entries are strictly positive, all the entries are positive. And when I integrate vectors which are all positive, I just sum a lot of vectors with positive entries, I get a positive vector. This is for any t larger than 1. So the conclusion is that xdb larger than xda for all t. This is exactly what we wanted to prove. So we see that if the Jacobian is Metzler and irreducible, then these two initial, when we take these two initial conditions like this, we get this. This is exactly the condition of strong monotonicity. Maybe we can write it like this: A, and just replace the order in here B. That's what we proved using the integration on W. So this is a kind of variational equation, just like we used in the analysis of conduction. It's a little similar. I want to look at the solution. What is the difference in the solution when I change my initial condition? Anyway, what this proves is that we have strong monotonicity. We just did a reduction to the linear case using the Jacobian. For the linear case, we already had a sufficient condition for strong monotonicity, which was irreducibility and Metzler. And now, in the 5 minutes that we have left before I have to go, I just want to show what this implies for the RFM. I want to show you that the RFM is a strongly monotone system. All this was relevant, is relevant for a lot of dynamical systems, but we concentrate here on the RFM. So let me show you that the RFM is a strongly monotone system. As usual, we will take the case of 3 state variables in the RFM, just so that I will have small matrices. I don't want to write everything in dimension n. So here I have lambda 0, 1 minus x1, minus lambda 1, x1, 1 minus x2, etc. And we already calculated the Jacobian. I want to show that it is Metzler and irreducible. So this means that I don't care about the diagonal entries. To show that the matrix is Metzler means to show that the off-diagonal entries are more negative. And irreducibility is related to the flow information between vertices, between different vertices. So again, I don't care about entry 1, 1 here, only about the other entries. So let me write them down. And now, what is our approach? So I need to show that this is Metzler and irreducible for any point x in the state space. My state space here is, of course, the 3-dimensional unit U. This is my state space. So let's look. How to test irreducibility. We know that we need to build the associated graph, mark edges according to where I have entries which are not 0. So let's mark the edges, the relevant edges. This is lambda 1, x1 from here. 1 to 3, there is nothing. 2 to 1, there is lambda 0, 1 minus x2. And 2 to 3, 2 to 3, there is lambda 2 x2, and 3 to 2, there is lambda 2, 1 minus x3. Okay, so now let me point out another important property of the RFM. I claim that in the RFM, if you start the n-dimensional cube, you immediately enter inside the cube for every positive t. I claim that after arbitrarily small time, all the state variables will actually be inside the open interval 0, 1. So I claim that xit will be inside this. Why? Imagine, for example, that x1 started at 0. To show you this, imagine that we started at 0. Then this is 0, and this is lambda 0, which is positive. So x1 t will be immediately positive. Yes, you see, when this is 0, this is 0. This is lambda 0 multiplied by 1. So a strictly positive derivative. So we are immediately pushed to positive values. And if I started from x1 0 equal to 1, what will happen? This is 0. This is minus lambda 1. So again, I claim that I will be pushed immediately inside the unit cube. So we say that the boundary of the unit cube is repelling. In other words, if you start on the boundary of the unit cube, you are immediately repelled from this and go inside the unit cube. So when you are inside the unit cube, this is positive, this is positive, this is positive, and this is positive, and you see a connected graph. Obviously, you can go here from any node to any node, from 1 to 2, and then to 3, from 3 to 2, and then back to 1, and so on. So once you are inside the unit cube, and this happens immediately, the graph is connected. So if the graph is connected, then this is irreducible. Now I can apply this theorem that says that if you are all the time measured and irreducible, then your system is strongly monotone. So in the RFM, if we have two initial conditions like this, the solution will satisfy the RFM. The solutions will immediately satisfy this. And you can try to understand the intuition behind this. It's very similar to what we spoke. This says that B is more jammed than A, but perhaps there is one entry where you have equality. Not in all of them, but in some entries you have equality. At least in one entry of B is larger than A, strictly larger than A. And this says that after time t, all the densities are now separated. All the densities here are larger than the densities here. So this is the meaning of strong monotonicity in the RFM. So this was a bit, I hope, not too much mathematics, just a little bit, and it was important for me to give the intuition. The next two talks will be lighter. I will not prove anything, just give you some statements and some examples, because I know it's late and Friday. Questions, please? Questions from the audience about strong monotonicity? All this appears also.
There are no questions from our side.
All this will appear in the lecture notes. In the final version of the lecture notes that I will send you in a few days, all this will be there. And everything else I talked about will be there. And actually, I should say thank you, Arvind, because I wrote here and there papers on the RFM, but now that I wrote these lecture notes, it's the first time that I have a more global view of the RFM and what we know about the RFM. So this actually helped me, and I also had organized everything. So this actually helped me to understand things better. So thank you, Arvind.
Okay, sir.
So if there are no questions, you will excuse me. I have to go and give a talk about admission here in the faculty. Today is an open day at Tel Aviv University for candidates who want to study engineering. And we meet again.
Yeah. At 2. At 2 o'clock, sir. Yeah. Thank you, sir. If there are no questions, then we will wrap up the session. Thank you, everybody, for joining.
Okay.